Hello everyone. Today we are going to cover the second fundamental postulate of electrostatic, which is the curl of electrical field equals zero. In a previous video, we talked about the divergence of electrical field and explained it all. I will leave in the description the link of this video. And now let's get started. Now let's start demonstration by giving the definition of the curl. As we see, the curl is the cross product between nabla or del vector and the vector field A, and it's by definition it's the dot product between the vector field A and some closed path. As we see, this path is vector and it's closed. We knew that it's closed because of this circle, or we can say that this path is bounded by some area. Then we divide this integration by the surface, by the area of the surface that we integrated around, and we make this area to be so small and we make it negligible and tends to be zero. Now you will have this question: what's the point of taking the curl of some point in the space? What is the meaning of the curl? We will discover this using these two illustrative examples. We have two vector fields. One of them is non-circulating and the other is circulating. I will start with this one, and I will apply the formula one by one upon this. Firstly, we took the dot product between this field and the path. I draw the path, and the path can be any arbitrary path, but I assume that this path to be rectangular in order to simplify. And this path is vector, so I express the vector to be counterclockwise. When we take the dot product between the vector field and the path, we are only interested about the points where the path are intersecting the vector field. So we have 6 points where we want to take the dot product around. I will start by this point. At this point, we know that our vector, that this vector has two components, y component and x component. And when we take the dot product between this x component and this path, the value is going to be 0 because this and this are perpendicular to each other. But this still, when you take the dot product between this and this, is going to give us some negative magnitude. So the dot product between each of them is going to give us a negative magnitude, and the downward arrow means that the resultant dot product is a negative scalar magnitude. And now let's go to the other point. At this point also, the y component vanishes, but x component still, which is parallel to this. And as these two components have a different direction, so it's going to give us another negative scalar magnitude. So, and regarding to this point, y component vanishes, but x component still. But in this case, both of them are pointing to the same direction, so it's going to give us some positive scalar magnitude. Now let's go to this point. At this point, y component vanishes, but x component is still, and the x component and the path have a different direction, so it's going to give us a negative scalar magnitude. At this point, y component vanishes and x component is still, and the path and the component have the same direction, so it's going to give us a positive scalar magnitude. And now let's go to this point. At this point, x component vanishes and y component is still. Y component and the path have the same direction, so it's going to give us a positive magnitude. As we see, in this case, the negative magnitude is going to eliminate this magnitude, and this positive is going to eliminate this negative, and this positive also is going to eliminate this. Each of them is eliminating the other, and we will end up with 0. And at this point, we understood what is the meaning of taking the dot product between the vector field and the closed path. It's telling us about the net circulations of this vector field around the closed path. And as the answer is 0, so this field is not circulating around this path. This vector is known to be conservative, or rotational. Now let's go to the other case. In this case, we'll do the same thing. We will take the dot product. We'll start by this path. I will take the tangent of this line. This line has x and y components. In this case, okay, I forgot to express the direction of the path. The direction of the path is like this. Okay, counterclockwise also. This consistent of x component and y component. At this point, x component vanishes, but y component still. But its direction is opposite to the direction of the path, so it's going to give us a negative scalar magnitude. Let's go to the other point, which is this point. I will take the tangent also. Y component vanishes, but x component still. And in this case, it's going to give us a positive scalar magnitude. Now, let's go to this point. At this point, x component is going to y component is going to vanish, but x component still, and x component and the x component and the path have different directions, so it's going to give us a negative scalar magnitude. Let's go to this point. At this point, we have x and y components. Y component vanishes and x component still, and it has the same direction. So it's going to give us some small positive magnitude, some small positive scalar magnitude. Now let's go to this point. Y component vanishes and x component still, and it has the component and the path have different directions, so it's going to give us a negative magnitude. Now let's go to this point, and I will take also the tangent. In this case, x component vanishes and y component still, and the direction of the component and the path is different, so it's going to give us a negative magnitude. So as we see, even if we have some positive values, we saw that the positive values resultant from the dot product between these two vectors with this path are so small when we compare it to these points, when we compare it to the other components. So it's going to give us some negative summation. Now this is telling us about the net circulations of the vector field around this closed surface, and as the magnitude is zero, this means that the field is circulating against to the circulation in the path. As we see, the circulation in the path is counterclockwise, then the field is circulating clockwise, and it's so obvious as we see. Now if we apply the rest part of the curl by dividing this by the area of the surface, then make the area to be so small and tends to zero, this is going to tell us about the net circulations of the vector field around some point in the space. And this is what the curl is telling us. It's telling us about the existing about this vector. It's telling us about the vector field if it's making a vortex. If this vector field is making a vortex or it's circulating around some point in the space, we will have a curl. And the direction of the curl is telling us about the direction of the rotation. And how to determine the direction of the curl? The direction of the curl can be determined by the right hand rule. All fingers is going to rotate with the direction of the vector field, and the thumb is directing to the curl direction. In this case, the vector field is rotating to this direction, so my fingers is going to rotate with this vector field, and the curl is going to be along my finger. As we see, the curl is inward to this paper, so the direction of the curl in this case is inward. Now let's go back to the curl of E. As we see, the curl of the vector field E is equal to 0. This means that the vector field A, E, or the intensity of the electrical field is irrotational and conservative. And this means that the net circulations of the vector field E, or the electrical field intensity, around some closed path equals 0. And when we apply Stokes theorem to this equation, we will apply it by taking the surface integrations for both sides. I will take the surface integration for the left hand side times ds equals 0 times ds. Of course, this is going to be 0, and according to Stokes theorem, this is equal the integration around some around the closed path for E field, around some closed path or some closed contour, and okay, this equals 0. This equals 0, of course. And when we draw, for example, some closed arbitrary surface, something like this, okay, and we have the vector field E, which is not rotational, as we saw before. The integration of the vector field around this closed path C is equal to 0. And let's, for example, divide this path into two small subpaths. This path, which starts from P1 to P2, this path is called C1. Okay, and this path, which starts from P2 to P1, let's call it by C2. Okay, according to calculus and the rules of integration, this can be it's the summation of two integrations. Firstly, the summation of C1 plus the integration around C2, okay, times dl is equal to 0. Transfer this to the other side, and we will end up with equal minus C2, forget C1, E times dl. Now let's complete the integration. This integration for path C1 is bounded by the point P2 and P1. Okay, by P1, it's initialized by P1 and ends at P2. And this is bounded by P2 firstly and P1, but because of the minus, the order of the boundaries, the order of P1 and P2 is going to be inversed. It's going to start from P1 to P2. E times dl. This equation is a form of Kirchhoff's law, and in other videos we are going to prove that the path integration for electrical field is equal to the voltage. And now let's sum up. By introducing the fundamental postulate of electrostatics in free space in their differential form and in their integral form. As the beauty of these equations that they are axiomal, and we will utilize the four of them, and we will utilize them in order to derive the other formulas we need in electrostatics. See you in another video.